So I'm going to continue with limit profiles. So I want to somehow consider a slightly different class of models. So in the talk by Evita, we focused on the case of interchange process. And in the following, I'd like to talk about some more projection of this interchange process and some variations of this projection, namely exclusion processes. And so let me say that what I'm going to present is based on two joint works. One is already out, and one is going to be soon on the archive. The first one, which is out, is based on a joint work with Jimmy Hay. And the second one, which is going to be out soon, is a joint work with Sam Olesker-Taylor. So the model I'd like to consider is the simple exclusion process. And now, in contrast to the interchange process we saw before, now we should think of our particles as being all indistinguishable. So remember, before we said we have a bunch of all distinguishable particles, and now we want to consider in the following just a collection of indistinguishable particles. But again, we have the same rule that every vertex of our graph, here in this case just the segment of length n, will be occupied by at most one particle at a time. Now, also, what I want to consider in the following is I really want to think about these particles as performing random walks. So what I mean by this is that each particle receives two clocks. The first clock will be an exponential 1 clock, or a collection of exponential 1 clocks. And the second will be exponential q clocks. So for some q between 0 and 1. Now, whenever one of the two clock rings, let's say for this particle here, the clock to the right rings, like this, then we think of this as attempting a jump, in this case to the right if the exponential 1 clock rings. And now this move is performed if and only if it is jumping to an empty site. So in this case here, we have the red dot as particles. We let it jump to the right, and because there's space, the particle can jump there. However, let's say the particle will again try to jump to the right, then we see the exclusion constraint in force, namely this move is going to be suppressed. And now, maybe also a bit in contrast to what Evita told, I'd like to consider different boundary conditions of the following. So I want to here in the following restrict myself to just the case where the underlying segment, where the underlying graph is the path, but I want to allow for different rules what happens at the boundary. So the simplest rule would just be looking at closed boundaries. So in this case, nothing can enter and exit the segment. Another case would be periodic boundary conditions, where whenever a particle at site n would jump out, it would just reappear at site number 1, again under the exclusion constraint. And the third case is open boundary conditions, which I'm going to define in the following. So let me maybe just illustrate in terms of periodic boundary conditions. So that corresponds to the case where our underlying graph is the circle. And as Evita said, already defining, looking at the interchange process on the circle is a very delicate question. But here in the following, we're looking at the projections of where we are just having the exclusion process on the circle. And so this is the same as thinking about periodic boundary conditions. And again, we have the very simple rule that each particle receives two clocks. And whenever, let's say, this clock rings, it tries to make a jump in clockwise order. And whenever, let's say, we have a particle like this and its rate q clock rings, it attempts to jump in counterclockwise order. Again, under the exclusion constraint. So in this case here, nothing. So this was for periodic boundary conditions. And now let me introduce the third kind of boundary conditions we want to consider in the following, namely open boundaries. So for the open boundaries, in addition to the clocks of the particles in the segment, want to allow for rate alpha, rate beta, rate gamma, and rate delta clocks at the boundaries. And the rule goes as follows. Let's say we are having here this rate beta clock, and it rings. Then whenever that clock rings and we have a particle at site n, we just remove the particle from the segment. And similarly, at the left-hand side, whenever the rate alpha clock rings, for example, we would try to place a particle at site 1. And if there's already a particle sitting, then nothing happens. So these are going to be the examples I want to consider in the following, and to give you a little survey on what is known and what is not known for these models in terms of mixing times, in terms of cutoff, and in terms of limit profiles. So just to clarify the setup, so let me introduce a bit of notation. So whenever we think about the simple exclusion process on a segment of length n, I want to treat it as a configuration eta t out of 0, 1 to the n at some time t, where you can think of placing a 1 at position x if at position x we see a particle, and a 0 if we have an empty set. Now this defines a continuous time Markov chain, which will be our simple exclusion process. And notice that it now depends on the boundary conditions we impose what we would like to take as our underlying state space. So we will either consider when the number of particles k, think of it as like a function of n, is conserved. We want to think of it as like the state space omega and k, where we have exactly k entries which are equal to 1. And this will be our suitable state space for closed and periodic boundary conditions. And we want to consider the space of 0, 1 to the n whenever the number of particles is not conserved, so in the case of open boundary conditions. So it's a simple exercise to check that in the case of closed and periodic boundary conditions, in fact, for any parameter q between 0 and 1, we have a unique stationary distribution mu n on the space omega and k. And let me maybe say here, we also allow q equal to 0, where I just want to say that there are no jumps to the left. So q equal to 0, you can just think of that there are only jumps to the right possible. And in the following, for open boundaries, we want to assume that our parameters alpha, beta, gamma, delta, and q are chosen in such a way that there's a unique stationary distribution on the space omega n. However, there's some very mild ways to make this work. So for example, if all the alpha, beta, gamma, delta are strictly positive, then indeed we can check that there's a unique stationary distribution. Okay, so this will be the setup in the following. And again, as in the talk by Evita, we want to consider like mixing times, so measured with respect to total variation distance. So just as a brief recap, in the following, we're going to look at the total variation distance of our exclusion process at time t from the stationary distribution in the different cases. And we want to look at what's the worst case distance at time t. So we want to just take the maximum over all initial configurations and look at this total variation distance from the stationary distribution at time t. And the mixing time, or more precisely, the epsilon mixing time for some epsilon between 0 and 1, will be the minimum amount of time t it takes until this distance, this worst case distance dt, drops below epsilon for the first time. Okay, so this is going to be our setup. And in the following, like to talk about the different cases, what do we know and what do we not know for the mixing time limit profiles for the simple exclusion process. And again, as in Evita's talk, if there are any questions on the model, on the setup, or whether certain results extend, just interrupt. I'm happy to answer any questions. Okay, so let's maybe start with the arguably simplest case, or say the case most like closest to what Evita was presenting talk before. And this is the case of the symmetric simple exclusion process. So let me start with the symmetric simple exclusion process on the circle. So here in this case, we want to just fix the number of particles k, and all the particles perform symmetric simple random walks. So they have two clocks, clock for jumping in clockwise order, clock for jumping in anti-clockwise order. And whenever the clock rings, they attempt to jump under the exclusion constraint. Now, in this case, we have a very good understanding of mixing times and even the limit profile. So it turns out that Lacwan managed in 2016 to show that when we assume that k is less than n/2, and the number of particles k goes to infinity with n, then if we look at the mixing time, turns out that it is of order n² log k, where the leading constant is given by 1/8 pi squared. And if we look at the limit profile, because we had this question earlier, it turns out that the correct window is order n², and we have an explicit description of the limit profile as using the arrow functions, the Gaussian arrow function. So let me maybe give a bunch of comments on this result. So first of all, we have the assumption that k is less or equal than n/2. I claim that this is not really a restriction. So in particular, I claim that the mixing time of a system with k particles is the same as the mixing time of a system with n-k particles. And maybe to see that graphically, the idea is that we can just swap the roles of particles and empty sites. So here in the picture above, we have like 4 red dots corresponding to like 4 particles, but equivalently, we can also just think of the white dots like a system with 3 particles. So this first assumption that k is less or equal than n/2 is not really a restriction. However, the second assumption is, so we do require that the number of particles k goes to infinity with n in order to really see a cutoff appearing. So you can think of maybe just k equal to 1, and as Evita mentioned earlier, the case k equal to 1 is just simple random walk. You can again talk about the limit profile. It will just turn out to be given essentially by the central limit theorem. But here we see that somehow this order n squared for the limit profile persists. And we also have like this explicit description in terms of like the leading order for the mixing time, where maybe if you wonder like, why is there a 1/8 pi squared? Well, that actually has something to do with understanding, again, eigenfunctions and eigenvalues. And having like maybe Evita's talk previously, it's not too surprising that they play a crucial role understanding the cutoff phenomenon or the cutoff time here. So in particular, if you check, it turns out that the exclusion process solves like a discrete heat equation. And if you check for what are the eigenvalues, eigenfunctions for like solutions of discrete heat equation, these are going to be sine and cosine. So this is maybe a bit explaining why you see an 1/8 pi squared here. But don't want to go into too much details here for the symmetric part, but maybe let me just give you some other result where we have a good understanding of the limit profile. And this is for the symmetric exclusion process with 2 open boundaries in the reversible case. So here we're considering a segment of length n. And remember, we have the particles can enter and exit at the ends of the segment. And it turns out that's a very recent result due to Gonçalves, Ciala, Marinho, and Meneses from 2023, that if we are in the case of a symmetric exclusion process, and we assume that the strength of our boundary rates is the same, so equal to 1. So what I mean by this is that alpha plus gamma is equal to beta plus delta. And in addition, we want to assume that the invariant measure is just the Bernoulli row product measure for some parameter rho between 0 and 1. So by Bernoulli row product measure, I mean that each vertex is independently occupied under the stationary distribution with probability rho for some rho between 0 and 1. Then we have a very good understanding, and let me maybe just phrase it here in terms of starting from the specific configuration 0, that actually we can here allow actually for any product measure as an initial state. That if we look at the time t theta, stated here is like 1/2 pi squared log n squared times log n plus 2 theta, then the total variation distance is explicitly given as the total variation distance between 2 normals. So we saw before in the talk by Evita that it was given, that the limit profile was given as a total variation distance for the random transpositions by Tessier in terms of the difference between 2 croissants. And here it turns out it's like the total variation distance between 2 normal distributions. But again, we have like this very explicit understanding. And let me maybe say that like in both the result by Hubert-Lacroix and in this work for the case of reversible symmetric simple exclusion process, so where we have this Bernoulli row product measure as our invariant measure, in both of these cases, somehow the trick is to say, okay, we can actually, even before we have converged to the stationary measure, approximate the distribution at these times t theta by a product measure, or by some measure, which we obtain by just tilting our invariant distribution. And somehow understanding this tilt is like the key how you get like these very precise results for the limit profile. So in the first result, it's a rather explicit computation. And here in the result by Gonçalves and others, it is using some entropy techniques. Okay. But so it turns out that to the best of my knowledge, that's it. So we had also previously the question what you can say more generally about exclusion process mixing times, and it turns out you can say a lot. So, but somehow the point is that in terms of limit profiles, as far as I know, these are the only 2 results for the symmetric exclusion process we have so far. So maybe just to give you like an overview, what you can say like more generally about mixing times for symmetric exclusion processes. So in the case where we look at the symmetric exclusion process on the closed segment, mixing time of order n squared log n is due to David Wilson in 2001 introducing something called the Wilson's lower bound technique, which is in some sense a refinement by the second moment method of Diaconis-Shashahani. And this like rather generally allows for proving a mixing time of order n squared log n. And you can also think about extending these techniques to different graphs, for example, set D, to provide very effective lower bounds. And also you can get like matching upper bounds of the same order. Now, in the case of open boundaries, this is joint work with Nina Gantet and Evita, where we could prove, like for general parameters alpha, beta, gamma, delta, that the mixing time is again of order n squared log n for the case of the symmetric simple exclusion process on the segment with open boundaries. And a bit more like after that, very recently, Justin Zalès actually managed to give a very nice proof for cutoff for, again, like reversible simple exclusion processes with reservoirs on general graphs. So it's very similar to the setup I showed to you before for the case of the segment with open boundaries, where we have exactly a Bernoulli row product measure. So whenever you have this on a general graph, Justin Zalès gives like a way to show cutoff for this. And also like for general parameters, alpha, beta, gamma, delta, strictly positive, like bounded away from zero, his student Hongquan Dran showed that actually cutoff occurs. But again, apart from the two results we saw that I just mentioned on the slides, we do not know whether, so we do not know the limit profiles. We have now a better understanding of mixing times, also of cutoff, but not of the limit profile. So maybe as a little illustration, just to show you somehow how these exclusion processes work. So not only talk about the limit profiles, you see here somehow that if we start off with an empty segment, let's say here, this is for the case of open boundaries, so all parameters equal to a half, and like n equal to 50, you can just simulate that and try to run the system. And maybe just to illustrate here, so this is about running it with like 50 steps a second. So you see it really takes some time, and it might be not so easy to see, okay, when is the system actually in equilibrium? So somehow you see at the very beginning, it's really out of equilibrium, but then somehow to determine like where this limit profile occurs, this is maybe not something you see immediately from the simulations. And maybe just to state again, because I guess Evita was also saying having some open questions, I'd like to have them rather early on. So maybe if you want, you can also think in the meantime, if you have some idea how to prove it. So we do know for the symmetric simple exclusion process on the closed segment, we do know that cutoff occurs. So it's like, again, of order n squared log k. So lower bound set is due to David Wilson, the upper bound is due to Hubert Lacroix. So it's like at order n squared log k with the leading constant of 1/2 pi squared. But we do not know what is the limit profile. And that might be somehow the next step to try to understand, maybe in this case, where we're still in a rather simple setup of just an exclusion process on a segment of length n, maybe closed boundary conditions, trying to understand what you can say here about the limit profile. Okay. So this is just like an overview for what you know for the symmetric case, and you maybe see that there's some similarities. Really, we can think of like the symmetric simple exclusion process as like a projection of the interchange process. Now, I'd like to move on and talk about now the asymmetric case. And this will be a bit more like very different from what Evita was presenting in terms of the interchange process. So here, I really want to make use of the fact that we have this parameter q, and I want in the following think of q being chosen between 0 and 1. Now, it turns out that also we have a very good understanding of mixing times and cutoff view, and in fact, also, I would say even a better understanding of limit profiles for the asymmetric case than for the symmetric case. And the reason is that there's integrable probability appearing. So here, please bear with me, we're going to talk about that theorem slowly. There's a very precise way how we can think about mixing times for exclusion processes in the asymmetric case, giving a connection to integrable probability. probability. And what I mean by this is that this is just like like a theorem, very recent one by Alexei Bufetov and Peter Nejad from 2022. So I mean by this that some of the behavior is very different, and there are some other distributions appearing. So before we had like the normal distribution and a Poisson distribution appearing, but now it turns out that if we look at the mixing time, so again, let me say that Q is between 0 and 1, so we are in an asymmetric case, and we assume that the number of particles K satisfies that K divided by N goes to some density parameter rho between 0 and 1. Now, if we look at order n with an appropriate constant, so here the square root of rho plus 1 minus square root of rho, everything squared. And if we now look at somehow a window of order n to the 1/3 and divide everything then by 1 minus q, then it turns out that if you look at the total variation distance, this will be given by 1 minus the cumulative distribution function of a trace-Witten GOE distribution. And maybe for those of you who are not so familiar with the GOE, so maybe a very brief description. It comes from random matrix theory. So if you take a Gaussian unitary ensemble and you look at what's the distribution of the largest eigenvalue and you do some appropriate rescaling, then this is the distribution you see. So somehow we suddenly, in the question about limit profiles, we see the appearance of some distributions we know from random matrix theory. And this is somehow, maybe somehow the flavor of using tools from integral probability, that somehow for like a particle system, here in this case, the asymmetric simple exclusion process, we see something which we somehow can identify with objects from random matrix theory. Okay, so let me maybe just let this theorem state here as it is and talk briefly about the history and some simulation, and then talk about the proof in a slightly different setup. So maybe also to say here, the question about mixing times, you can ask for this model or for like related models, and this is not a question like, well, the limit profile results are very recent, but some of the overall question about understanding mixing times is much older. So some of the first studies of looking at mixing times for the asymmetric simple exclusion process go back to Benjamini, Berger, Hoffman, and Mossel, 2005, who proved that the mixing time is of order n for the ASEP, and also what they call the metropolis shuffle. So maybe giving it a bit in the context of the interchange process, you can just think of it as like introducing back the colors. So I want to think of this as like a colored ASEP, where in particular all the particles are again distinguishable. So you can think about it as like an interchange process, but somehow with at rate 1, you sort the respective labels in order, and with rate q, you somehow reverse sort the labels. So just wanted to mention that this can also be done like for this color version of that. Now, in terms of the mixing time, there's also now a nice alternative proof for the ASEP that the mixing time is of order n using path coupling due to Greenberg, Basco, and Randall. And in fact, somehow again by Hubert-Lacroix, joined with Cyril Labbé, he managed to show that also the ASEP exhibits cutoff, and the same holds also for this colored version. So the biased Cartman, also called metropolis shuffle. And as I said, I want to somehow just give like the bigger picture in terms of what we can do nowadays. So very recently, Ling-Fu Zhang proved that the limit profile for the metropolis shuffle is actually given by a commutative distribution of a tracy-Witten GOE. So that's, again, the same story. You look at the largest eigenvalue, but now of a Gaussian orthogonal. Okay. So some of the pictures here for the asymmetric simple exclusion process very differently. And the reason is maybe the following. So before, in the symmetric case, you can check, we were somehow looking at things which spread out. So in particular, on the closed segment, the distribution is just the uniform distribution on a state space. But now if we look at the asymmetric simple exclusion process, the stationary distribution looks very different. So that was again starting just from the closed segment with all the particles on the left-hand side. But you see, as more we run the system, all the particles will essentially pile up only on the right-hand side. So the stationary distribution is very, very different from just particles being symmetrically spread out. So let me maybe let me run that thing once again. So if we start off with all the particles packed on the left-hand side and we have a drift to the right, then we really see the particles will spread out and they will start to accumulate on the right-hand side. So somehow the stationary distribution for the OWPS is very, very different from the stationary distribution we saw in the symmetric case. And that maybe explains why also we see like this very different behavior. So no longer mixing times of order n squared, log n or log k, but really mixing times of order n and like a cutoff window of order n to the 1/3 in this case. Okay. So let me maybe now come to like a version or like a variant of this model, namely the asymmetric simple exclusion process with open boundaries. And in particular, I want to, in the following, only consider the case where we have one open boundary. So you can also ask what's happening in the case with two open boundaries. And in fact, the answer is we don't know. So that's another open question. But in the case of one open boundary, so where we have a rate alpha clock for particles to enter at side one and a rate gamma clock for particles to exit, we now have a pretty good understanding in terms of the mixing times and also in terms of the limit profile. So let me start maybe by talking about first the mixing time. So in this case, where like beta and delta are equal to 0, and let me say here alpha and gamma are strictly positive, it turns out that the mixing time is of order n and that cutoff occurs. Again, this is based on joint work with Nina Gantet and Evita. And we have a very explicit way to identify the constant, and this involves this parameter a, which is like a function of the parameters q for the bias, alpha, the rate of particles entering, and gamma, the rate of particles exiting at side number. And maybe what's the intuition behind this, as you can imagine, maybe from the picture, and I'm going to show a simulation in a second, is you want to start off with empty initial condition, and the mixing time is essentially the hitting time of the configuration where everything is full. And how do you somehow get from this empty initial condition to this full initial condition? Well, somehow the only way is that your particles will enter at the left-hand side. So we can think of the left-hand side as being a reservoir of particles, and we can assign to it an effective density. So this effective density, I want in the following call just rho. So you should really think of somehow extending here the segment towards infinity with just a constant, so like with a Bernoulli product measure with parameter rho. And you can check that rho should solve like this quadratic equation. So the number of particles arriving at side 1 should be like proportionally to alpha times 1 minus rho. So somehow alpha for the rate of particles entering, 1 minus rho because you want that this side is empty in order to have a particle arriving, plus q times rho times 1 minus rho. So at rate q, a particle from side number 2 jumps to side number 1. So this gives this factor rho times 1 minus rho. And this should be equal to gamma times rho. So the particles somehow jumping out from side number 1 to the reservoir, plus rho times 1 minus rho. So the particles jumping from side 1 to the right. And so if you solve this and take the positive solution, you just arrive at rho at this specific form here. Okay. So now it turns out that this parameter rho here, this effective density, which just gave you like somehow as a motivation, plays a very crucial role when understanding somehow the mixing time. So you saw before with the parameter A, but also here somehow, whatever is this effective density here, you will really somehow see that this turns out to be like the key amount, just telling you how much time you have to spend until somehow your particles have entered. So somehow the main idea will be to say, okay, what can we say about like the number of particles which will enter here at the left-hand side? And you see here, again, as in the case of the closed segment, particles will just pile up on the right-hand side. So really what we really want to understand is like, what's the amount of time it takes until we see here n particles entering the system. Okay. And so for the previous results, we were only interested in like what's the leading order. So this is something you can do using, let's say, ergodic theoretical considerations. But in fact, and this is now what I'm going to present, we have a very good understanding now also what's the limit profile. And this is said earlier based on joint work with Jimmy. Now, in the setup, we do want to assume that, so we have to assume that alpha is strictly greater than gamma. And again, we just have like particles entering and exiting at the left-hand side of the segment and nothing entering and exiting at the right-hand side. Now, if we define the time t rho as a function like this, so again, we have like a leading order term. So it's going to be 4n in the case where rho is greater or equal than a half. And it's going to be n divided by rho times 1 minus rho for the effective density from before when rho is strictly less than a half. Now, in these two cases, we can then somehow recenter. So we can then look at the profile and we somehow see different distributions appearing. So let me maybe say here, what's important is that we are looking like somehow at two different windows. So it turns out that in the closed segment, we always had like an n to the 1/3. But in the case with like one open boundary with the reservoir, there will be like the regime where rho is like greater or equal than a half, where actually our window will be of size n to the 1/3. And there will be the case where rho is strictly less than a half, where actually our window turns out to be like n to, like square root of n. So in some sense, what we get here is like a mixture between, like, say, a Tracy Whittem or like a KPZ type behavior, you would call it, where some of these distributions like a GOE and a GSE. So GSE is just coming from a Gaussian symplectic ensemble. No worries what it is. If you know it, good. If not, it is just some distribution again appearing in random matrix theory. It turns out that somehow, depending on what's your strength of the reservoir, so either like being greater or equal than a half or being strictly less than a half, you see one of these distributions appearing. Okay, so again, what's the punchline? Well, in the case of the asymmetric simple exclusion process with one open boundary, we also have a very good understanding of what's the limit profile, and somehow it's even a bit more interesting in the sense that we have like this jump around a half, where somehow we have the transition from like a window of order n to the 1/3 to a window of n to the 1/2. But maybe so to say, where does this come from? And that's going to be like the ideas of the proof. And let me say here that this is also going to be like following a similar line as the arguments by Bouvetoff and Deja. So actually our process, which we will use in order to show like these limit profile statements, is that we are looking at an asymmetric simple exclusion process, but now on the half line, so just on the natural numbers. And in the following, so I'd like to consider the case where, again, we have like rate alpha clock for particles to enter, rate gamma clock for particles to exit, and we're looking at the half line. So what that means is like we're just looking at the natural numbers, so we're extending like our segments like towards infinity to the right. And the key quantity, as we have seen like in the simulations and intuitively, is we just want to count what is the number of particles we have in the system at time t. And we're in particular interested in, like, say, start from empty initial conditions. What is the number of particles jt, which we have after time t? And somehow, if you look at the following theorem, that maybe explains somehow how we get the limit profile. So this is a very nice, very recent work by Jimmy Hin. And it says that if we look, again, under our assumptions from the theorem for the limit profiles before, if we look at what's the number of particles jt entering the RCEP on the half line, then we actually see that, okay, it satisfies law of large numbers, and it also satisfies here this convergence theorem. So if we, in the case where rho is strictly greater or equal than a half, when we normalize with t to the 1/3, we can find like constants mu and sigma, such that if we look at what's the probability that this quantity is less or equal than s, then this will be given by just like these Gaussian symplectic ensemble, so the cumulative distribution function of the Gaussian symplectic ensemble and the Gaussian orthogonals. Okay, and like again, in the case where rho is less than a half, it turns out that if you look at what's the number of particles which have entered the segment, it has like a central limit theorem type behavior. Okay, So this is somehow what we use as a key input, and having like this precise results available, which is a very nice theorem using really very deep insights from integral probability, you can use like some of these insights in order to then give a statement about limit profiles. So let me maybe just give you a rough outline how we do that. So in the case, so again, this is like for the case with one open boundary, and it's similar. So this technique was first given by Buffetov-Nejat. So in this case, we just split our proofs like an upper and lower bound separately. So we somehow do not use some like approximation as in the symmetric case once, but we somehow treat the two bounds separately. And I claim that the lower bound is actually simpler in the sense that we just look at what's the number of particles entering the system, and we just count. And if this number is too low, we saw before that the stationary distribution is very much just concentrated on like everything being packed, then we just conclude we are not in stationarity. And the upper bound is a bit more tricky, and I'll maybe like briefly talk about this. Okay, so let me maybe just give you like the statement a bit more precisely for the lower bound. So in this case, what we do is we start just with empty initial conditions, and it turns out that there's a very simple coupling argument to say that actually, if you look at the RCEP on the finite segment, you can just couple it with the RCEP on the half line, such that you guarantee that starting from empty initial conditions, the system on the half line has always at least as many particles as the RCEP on the finite segment. Okay, and this coupling just goes like somehow you pick the same particle whenever possible, and there might be a case where somehow your last particle somehow gets stuck in the finite segment, but then somehow your half space RCEP just has more space to let this particle move. Okay, so that's just in a nutshell something we can achieve. And now the event we're going to look at will be something of the following form, namely you just wait until n minus some small number. So for the proof, we take like log to 1/16 times n, but it's not particularly important, but just like some very small number, but still like diverging with n. Then you can check that for this event, some of the probability and the stationary distribution to have like at most this many particles goes to 0. And somehow we use this together with the theorem by Jimmy to somehow give a lower bound on the distance from the stationary distribution. Okay, so this is like just strategy for the lower bound, and for the upper bound, it starts off similarly, but then takes a slight twist. So again, we can show that in fact, starting from the empty initial condition, it's just enough to wait until your entire interval is full. So this is like not a difficult argument to make rigorous, that if you start from the empty initial condition, your distance from the stationary distribution is bounded by like the probability of Tn being larger than T, where Tn is like the first time that the interval is fully packed. Okay, so if you look at this, then let's just wait until somehow like an interval of the form log to the power 1/16 n comma n is full. So like almost the entire interval is full, apart from maybe the first log to the 1/16 n bits. Then you can actually show that somehow starting from this, somehow very shortly after that, you're actually really completely. But actually, this like slight slack of like the first log to 1/16 n many positions is already enough to give us somehow some way that we allow for certain errors. And what I mean by this is that, in fact, if you remember like the theorem by Jimmy, this is really requiring that we start like with empty initial conditions. But in fact, what we want is we want to somehow say, okay, we look at this event BT, but we want to look at it not from empty initial conditions, but we want to look at on the half line with the initial condition that each side larger than n is actually initially occupied by a particle. Okay, but how do we now take like some of this theorem, which only works for the case of empty initial conditions for the half line, and make it into a theorem working also for the case where we have a non-trivial initial condition? And this is used like a technique called color position symmetry, which is a very nice insight. I think first goes back to Amir Angel and Balko for the case of the so-called tacit speed process. And this color position symmetry term was then made more precise and like further developed by Alexei Borodin and Alexei Bufetov. And roughly speaking, what this says is that if you want to consider the RCEP started from empty initial condition, but you have some different initial condition where like all sites larger than n are initially occupied, you can actually do the following. You can start with your empty initial conditions, let it run, and then do some non-trivial steps, some non-trivial random operation for the RCEP afterwards. In order to make that work, you actually have to go to the colored RCEP. So somehow think again of it like as the interchange process, but so somehow all the particles have labeled, but we're not like swapping just labels, but we do like this at rate 1, you sort the labels, at rate q, you reverse sort the labels. And if you use this like colored version, then there's a way to make this rigorous, that somehow instead of starting with instead of starting with this like initial condition with everything after n being packed, you start with empty initial conditions and you do some non-trivial moves afterwards. And somehow this very slack at the very beginning we're left to ourselves allows us to make like these steps at the very beginning to somehow encode this non-trivial random operations in a very nice way, such that we only like barely modify the system. Okay, so maybe this is just like to give you an overview. Also let me maybe say briefly that this color position symmetry is related to something called random walks on Hacker algebra. So you somehow treat the exclusion process, the RCEP, as a random walk on a certain Hacker algebra, and that's has a certain like involution property which allows you to do this non-trivial shift. Okay, but that's maybe just for the experts at that point. Okay, so what do we do? So just to maybe sum up in this case for the simple exclusion process on the segment. So we do have like the world of the symmetric simple exclusion process where we know we have like this convergence to like a Gaussian profile where we do some approximation techniques. And we have like these tools from integrable probability coming in for the RCEP. So for the asymmetric simple exclusion process on the segment. And maybe let me use the remaining maybe like 5 minutes to just give you like a brief outline that we can also say a bit more on other graphs. And this maybe brings back like somehow or loops back to Evita's talk. So remember we had before that we looked at the interchange process on the complete graph and can study limit profiles for this one. You can ask, what can you say about maybe the simple exclusion process on the complete graph? And so let me say that this is just maybe in a nutshell. So what I'm going to say now, this is like a work in progress together with Samuel Esker Taylor. So maybe to loop it back, so this is the simple exclusion process on complete graph, and as having the setup as Evita had in the talk, we want to view it in discrete time. So we pick like an edge uniformly at random, let's say here. And again, we forget just about the labels, but we have like either particles here in red, which are all indistinguishable, or empty sites. And what we do is we pick an edge and we just swap. Okay, so we are back to like a reversible setup. Now, again, if we would like pick an edge and we would see two particles, two empty sites, then nothing would just happen. Now, in this case, it turns out that also mixing times and cutoff are very well understood. So in the case of the symmetric simple exclusion process on the complete graph, again, under the assumption that k is less or equal than n over 2, the mixing time was studied by, again, Lacroix and Leblanc in 2010 already, that, and the result says that if you look at the mixing time, then it is of order n log minimum of n and k squared, and the constant up front is just a quarter. And again, like proving this result, so in the case where k is of order n, that already goes back to the 80s due to Diaconis and Sheshahani. And let me maybe say at this point also that this is like a model where equivalently you can think about it as so-called Bernoulli Laplace urn. So this is in fact equivalent to the simple exclusion process on the complete graph when talking about mixing times here. So, and this is maybe like the statement by Diaconis Shoshani that was maybe more thinking in terms of the EARN models, and again, using really more the approach as presented by Evita. But it turns out that somehow you can actually give a different perspective on it, and which has something to do with using approximation by diffusions. So let me maybe give you the results. So it turns out that we are also able in this case to determine the limit profile, so together with Sam. And it turns out that it matters like what is the ratio of k divided by square root of n. So if this goes to infinity, as n goes to infinity, then we actually see again like a total, the limit profile is again just given as a total variation distance between two Gaussians. In the case where k divided by square root of n goes to some constant, non-trivial constant between 0 and infinity, the limit profile is given as a total variation distance between two Poissons. And whenever k goes to 0 with n, then it turns out the limiting distribution is just given as like the CDF of a Gumbel distribution. Okay, and maybe for time reasons, let me just mention here very briefly how do we do that, but without too many details. So it turns out that you can just, instead of looking at this process, you look at a birth-death process explicitly given. And for this birth-death process, so it was already shown by Laquan and Leblanc that it is, so studying this, the total variation distance for this process from the stationary distribution, this is the same as like looking at the, at like somehow the law of the simple exclusion process on the complete graph. And then what we do is we're actually showing that you can understand this birth-death process very well by like approximating it using Ornstein-Uhlenbeck process in the case where k is growing much faster than square root of n. And in the case where k divided by square root of n goes to a constant kappa, you can actually show that it converges to an infinity Q. And somehow the Gumbel special case, somehow this infinity in some sense reduces to just a coupon collector problem. Okay, so this is maybe just to give like a brief overview of what we can do also in the case of the complete graphs, and we're looking back to the talk by Evita. So let me maybe sum up. So in the case of the exclusion processes, we have also now rather good understanding of the limit profiles, however, just like in some very special cases. So in the case of the symmetric simple exclusion process, we have a good understanding of the limit profile for the circle, for the open boundary when we're in the reversible case, but somehow it feels like there should be a good, there should now be a good time to make also some progress, also understanding limit profiles for the closed segment, and maybe even hoping for more general graphs, in fact. Now, in the case of asymmetric simple exclusion process, we also have a very good understanding in the one-dimensional case, and the reason is that we have a connection to integrable probability. So we have like this very powerful set of tools, understanding like what's the number of particles entering the segment, where we have like this Tracy-Widom distribution, sort of from matrix theory showing up. And it turns out that this is somehow giving us like a different way to understand limit profiles for exclusion processes. And somehow like a third approach, if we look at the simple exclusion process on the complete graph, where we have like this phase transition from a Gaussian to a Poisson to a Gumbel, somehow the idea is to use like an approximation by a diffusion. So, or like approximation by like Ornstein-Uhlenbeck or infinity Q to be precise. So somehow there, we also have like a very specific way how to attack like the question of limit profiles in this case. But again, as I said, we understand it now better, but there are there's still many open questions. And as said by Evita, we would like to have a much better understanding what happens like in various cases, in particular also